This is a short talk about yet another "here we go again" moment when I came across an article in Scientific American from March 2018 entitled "The Sun is Spitting Out Strange Patterns of Gamma Rays and No One Knows Why." I did not know much about the subject, but I silently made a bet with myself that 1. The existing theory of gamma rays from the Sun would be based upon gravity and random motions. 2. The new improved data would completely contradict the predictions of that gravity model. 3. The article would bring in dark matter and a few quotes to the effect of, "We are completely surprised by what we are seeing. Maybe there's new physics here." And 4, of course, nothing would be said about a possible electrical explanation. This was admittedly a somewhat cynical wager, yet I did win the bet on all 4 accounts. I reviewed Don Scott and Hannesa Альвен's models of the Sun's electrical connection to its larger environment, and I had some discussions with Uollesom Tornhillom about the gamma ray data. The Sun puts out very few gamma rays. It seems there are very few gamma rays in the entire universe, at least in comparison to the number of photons that we see with our eyes. Gamma rays are a type of light which is very, very energetic, billions of times more energetic than the photons of light that power photosynthesis and average biological processes. The recent papers from 2018 and 2019 summarize 10 years of gamma ray data from the Sun taken by the Fermi telescope. Let's see how well the standard model prediction stacks up against the published data. I made a little chart. On the left are the basic questions, and then the standard model and the data. How many gamma rays would we expect to see from the Sun? The standard model predicts a certain number that would be observed. The data shows we see anywhere from 10 to 100 times more than was predicted based upon the energies. Where should we see the gamma rays come from? The standard model says that the rays should come from the sunspot regions. What do we see? Well, the rays come from the entire disk, and also from around the Sun, and also from above the poles of the Sun. What distribution of energies would we expect? The standard model says that the spectrum should be smooth and weighted with very few high-energy gamma rays. The data shows far too many high-energy rays and a clear gap in the 40 to 50 giga-electron-volt range. When, during the solar cycle, would we expect to see the gamma rays? Standard model says there should be more gamma rays during solar maximum, when there's more sunspots. The data shows just the opposite. And would we see gamma rays from solar flares? The standard model says no, and the data says yes. To quote a few of the authors and reviewers, Brian Fields, a particle physicist from the University of Illinois, says, "It's amazing that we were so spectacularly wrong about something we should understand really well, the Sun." Tim Linden, a particle astrophysicist at Ohio State who helped analyze the data, said, "The 40 to 50 giga-electron-volt dip just defies all logic." And Meir Unissa at Michigan State University said, "Analysis of 9 years of data collected by Fermi LAT from the Sun revealed a very bright, steady emission of gamma rays at energies above 100 giga-electron-volts. That contradicted all theoretical expectations." What is this standard cosmology model that is so spectacularly incorrect? It is a model built upon isolation and random destruction. This model says that our Sun, like every star, is energetically isolated from all other stars. It says that stars like ours cannot produce any gamma rays of their own from their surface, and hence any observed gamma rays coming from the Sun must be coming from somewhere else. In this model, if the Sun cannot make its own gamma rays, then where can we look? The phenomena to the rescue are cosmic rays. Cosmic rays are a bit of a mystery. We observe very high energy particles impacting the Earth from all directions, and we call these cosmic rays. They are known to come from pulsars like the Crab Nebula, but that one clear observational fact is usually greatly downplayed in favor of the standard model description of cosmic rays, which says that they come from the most cataclysmic events imaginable, like dying, exploding superstars, and colliding black holes, and colliding and exploding magnetars, and colliding, exploding galaxies. You get the picture. The Standard Model paints a picture of our isolated sun in a sea of debris generated from random destruction. Occasionally, a stray bullet from this mayhem will ricochet through a sunspot magnetic field and be flung towards the Earth. As already said, every prediction of this model was incorrect. The data is fascinating. The solid circle in the middle is the disk of the photosphere. The outer dashed circle is the outer limit of where they collected the data. Each dot is a gamma ray detected. The left two panels are from solar maximum, when there's many sunspots, and during which the previous model predicted there'd be more gamma rays. The right two panels are from solar minimum, where there are few sunspots, and the previous model predicted there would be fewer counts. I am struck by how little data there is. Over 10 years, and we have only a few hundred data points? These solar gamma ray events are very rare. I admit the telescope is very small and very far away from the sun, but still, compared to the gazillions of visible light photons coming off the sun every second, gamma rays are rare events. How might this data make more sense if we include electricity in our cosmology? If we pull back and look at the filaments of the interstellar medium, all stars and planets are very, very small specks on much larger filaments. The distance scales here are difficult to comprehend. Do you remember those comparisons? If the entire atom were the size of a football stadium, then the nucleus would be a golf ball in the center. Those are the sort of sizes we need to imagine for stars in galactic filaments. I will try a metaphor using cities here on Earth to understand the sizes involved with the filament model. Imagine the galactic filament is the high-tension power lines connecting entire cities on Earth. If we zoom into one city, that is the region of the filament where our sun lives. Zoom in further to a football stadium in that city. That is the full body of our solar system. And then all the planets and the bright disk of the sun, what we usually think of as our solar system, are all contained in that little golf ball in the center of the stadium. From this, how then do we get 10 billion electron volt gamma ray bursts? Does this mean that the galactic currents have this kind of voltage? No, not at all. Think about lightning on Earth and about the upward shooting sprites and elves. The Earth's global electric circuit only sustains a few 100,000 volts between the ground and the upper cloud layers. Yet, in a strong thunderstorm, we see gamma rays corresponding to many millions of volts. How do we explain this apparent contradiction? Where did the energy come from, since locally there is only 100,000 volts between the cloud and the ground? As Alfvén pointed out, in a distributed electrical circuit, such as the electrical grid for a town, the energy from the entire grid can be released at one small point during an explosive breakdown. The transformer might only have 1,000 volts across it, yet when it explodes, it releases electrons with millions of volts. How? Because the transformer is just a small piece of a much larger circuit. The same explains how sprites and elves above storm clouds can send gamma rays out into space packed with billions of volts. If you read the existing literature about elves and sprites, the explanations are stuck on exactly this point. They are not including that the burst is part of the entire electrical circuit of the Earth. The same applies to the sun. The surface of the sun and the corona of the sun are all connected to a much larger circuit that includes and reaches beyond our visible sun. Explosive releases in the form of gamma rays can happen inside of that photosphere surface. They can happen above the surface, or even several radii away from the sun, because the electrical body of the sun extends out to the heliopause and is connected to a circuit that reaches to the neighboring stars. The filament model predicts that we should see at least some high-energy events analogous to the strongest lightning on Earth. Studying the Earth gamma rays will teach us how to better understand the sun's electrical environment. What about the polar component? The authors say that there is a steady source of gamma rays coming from the polar regions of the sun. In the standard model, this is unexplainable because the standard model says that above the poles are weak magnetic fields that are relatively straight. Hence, they would be unable to bend cosmic rays. But in the electrical model, stars are connected through their poles to larger filaments that stretch for many light years, connecting multiple stars into one larger circuit. Charged particles flowing towards stars would have a very long running distance along these smooth magnetic field lines and be capable of picking up very large energies. In the electrical model, we would expect to see a relatively constant source of high-energy emissions coming from the polar regions, which is exactly what the data shows. The authors further describe an equatorial component of the data. I do not see that so clearly, and I think maybe they are holding on to the standard model, which says that there should be something special about the sunspot region. It looks to me that the rays are coming from a sheath that surrounds the photosphere. It looks to me that the gamma rays are not at all limited to what we would call the surface of the sun. The data is spread out around the sun. This region around the photosphere is where atoms become stripped of their outer electrons, which is usually interpreted as thermal heat. Contemporary astronomers look at the ions around the sun and say that the corona must have an enormous heat and temperature of millions of degrees. But this stripping of electrons could have an electrical or even a chemical cause and not be related to anything like temperature as we have defined it on our cold, wet planet. Remember, you can strip electrons off of water with a 5,000 degree oven or with a 9-volt battery at room temperature. According to Don Scott's model, which builds upon the model of Hanness Альвен, our star is powered primarily by a DC current that flows into both poles of the sun. This DC current also has a ripple where the current rises and falls slightly over a 22-year cycle. This 22-year ripple in current is connected to the 22-year solar cycle where sunspots come and go and the polarity of the sun's magnetic field flips. The 22-year cycle is not necessarily coming from the outside, nor coming only from the sun, but is more likely a result of the interaction between the sun and the larger filament. We can draw a simple graph of the electrical current powering the sun. The blue wavy line represents this current feeding the sun. The current does not go positive and negative like an AC current in your house. The current is one directional, but has a strengthening and a weakening. In other words, an AC ripple on top of a predominant DC current. For example, the sun might have a current oscillating between 10 billion and 11 billion amps. On the diagram, I have circled in red the maximum and minimum of the wave. Here the current to the sun is steady. It does not change much. We are in solar minimum. The magnetic field of the sun is smoother. Now there is longer running room for particles to be accelerated towards and away from the sun. We would expect higher gamma ray output. I have boxed in green the places where the current to the sun is changing rapidly. Here we are in solar maximum. The magnetic field of the sun is agitated by the quickly changing current. Electrons flowing towards the sun at this time are caught up in the smaller circuits and cannot so easily reach gamma ray energies. The electrical model agrees with the Fermi telescope data. What about solar flares? According to the standard model, solar flares cannot reach the 100 giga-electron-volt energies that are seen by the Fermi telescope. Yet several of the data points happened exactly during large solar flares. The authors are perplexed by this coincidence. I would again point to what we know about lightning on Earth. If the Earth can produce gamma rays in electrical discharges, solar flares can easily reach hundreds of times those energies. What about the number of gamma rays we see? The standard model is short by a factor of about 100. Remember, the standard model says that the gamma rays are only produced when a background flux of cosmic rays randomly interacts with the surface of the sun. For this model to so clearly get the number wrong means to me that the gamma rays are simply not being produced in this way. This again is clearly better described by the filament model, where stars are fed by concentrated rivers of energy and not some random background. We will have to build out different solar electrical circuit models and see which circuits give the observed number of gamma rays. Lastly, we can ask about the dramatic absence of gamma rays in the 40 to 50 GeV range. I do not have much to say about this one. Usually, when we see a missing energy range in an emission spectrum, we look for some specific process that would absorb just that energy. This energy is tantalizingly close to the mass of an iron atom, which we know has a special place in nuclear transmutations. But I really think that this gap will point us to something that no one has yet imagined about basic solar physics. I can understand if you did not closely follow all my explanations. Like me, you probably had never before looked at gamma ray data from the sun, so you are still wrestling with the vocabulary and how pieces fit together. The existing model used by astrophysicists predicts everything incorrectly. But the journals and the reviewers cannot come out and say such a simple fact, and instead must contort themselves around dark matter and possible new physics. I think some old physics, called electricity, can help us think through this gamma ray mystery. It seems to me that the electrical filament model of stars does a particularly good job of explaining why we see 100 times more gamma rays than the random model, and why there is a steady polar component. I also think the filament model explains the distribution of gamma rays in a sheath surrounding the photosphere. There's plenty of quantitative work to be flushed out in all this. I'd be happy to help someone tackle that. Thanks again to Wal and Don for helping me think through these ideas.